going live. Excellent. Right. And now we're live on YouTube as well. Hi, my name is Oleh, and I'm very happy that you're watching Virtual Job. I'm not sure if the YouTube now will stream whatever was streamed before, but let me repeat that. It is doing that?
Yeah, it is. Great.
So now we are like, there is a 2-minute delay.
Yes, kind of.
Very good, very good. I'll be your audience. So anyway, back to the necessary information. So thank you, Virtual Jock. Thank you, Grolvium. Thank you, Snick. If you have any feedback or you would like to join the live discussions of the sessions, join the Virtual Jock Slack. Hashtag live session is the channel. And of course, share the group or this particular session with your peers, with your colleagues, with anyone who is interested in the state of the reactive systems. And if you have any feedback, and the most sincere piece of feedback is, of course, following us, then the Twitter @VirtualJack or @Shalife if you want to communicate with me personally. With all that out of the way, we're going to start with today's session, which is the state of reactive streams by Oleh. You can find Oleh at Twitter as well, so you should absolutely join and follow him. Because if you will not be able to ask any questions during this stream, which I will try to forward to Oleh, then you should ask them online. And he'll be absolutely happy to respond to all of those. So this is the necessary information. If the video quality on YouTube is not up to your expectations, you should use the cog icon near the widget, right? And the quality should go at least to, I think, 720p. So do that. And please allow me to welcome Oleh. Hey, how are you doing?
Hey, so yeah. First of all, thank you for inviting me to the virtual jog again. It's my pleasure to be in there for the second time and talking about my most lovely topic, reactive, of course. And let me share my screen first. Do you see me? Do you see my screen?
I can see it. I can see it. I can hear you. The stage is yours.
Perfect. So slides is on, right? All right. I hope.
Yeah, it's all good.
You can see everything. And welcome to this session, which is about the state of reactive streams. And first of all, let me introduce myself really quickly. My name is Oleh. I'm from Kiev, from Ukraine. If you have never been to Ukraine before, I'm really welcoming you to come to our country, to Kiev. We have tons of cool conferences and different meetups, so you can combine and join in the country and the city, along with learning something new about Java and technologies. I work for Netify. This is a technology company. We are building actually the future of reactive streams, which is RSocket. I'm briefly cover RSocket and what it is during this talk, but we are not going in depth. And I'm one of the contributors to Project Reactor. So I really hope, I contributed to reactive streams and reactive programming, and I hope I have credibility to talk about the state of reactive streams. This is basically about me. And let's go straight forward to our agenda and what are we going to cover during this presentation. So today we are going to talk about the story of reactive programming, because in order to understand what is the state of reactive streams and what's going on with reactive streams at all, we have to understand why people created reactive programming and reactive streams. So this is the main question that we're going to cover. So it's kind of history of reactive programming and reactive at all. Then we are going to switch to the state. We're going to talk really quickly about the programming, the libraries, in general, the expansion of reactive streams on all platforms in different languages. And finally, we are going to talk about what is the future of reactive, whether we have reactive in the future or we won't have anything related to reactive and we will be good with imperative programming. We don't know what happened, but we are going to talk about this a little bit. So if it's good for you, let me quickly start with the main word of this presentation. Reactive is all about interaction. Basically, it means that you have to react to all the events. And from the history perspective, the first mention of word reactive it is in the context of reactive system. And basically, reactive system is a type of system which react. So it's nothing more. It's just a system which reacts. And you may wonder, and the main question, the first question in your brain that could pop up is, what is the difference between non-reactive and reactive system? So in order to understand that, let's welcome our main character of this presentation, which is Goose. So Goose is displayed on the bottom of the screen. And Goose is basically a bird. It's a duck. Yeah, you know it very well. And in order to understand non-reactive system, let's try to understand a couple of inputs to the Goose. So imagine that many people are, or I don't know, the owner of Goose is asking him to do that and to do this and to do something else and to bring that and this, like you ask your dog. But Goose is a simple, straightforward bird. It does only one thing. It eats. It eats whatever it eats, and it produces, you know, what it produces in the result, what everyone is producing afterwards. So basically, non-reactive Goose and non-reactive system is basically ignoring all the inputs and focusing only on the one things which is the most important in their life. For example, the food. So Goose consuming food and ignores all the commands because Goose is just simply eats and produce, you know, what it produces. So basically, non-reactive system, for example, in microservices world, is the system that doesn't take into account all the changes in the environment. For example, one service is disappeared or external system doesn't work right now. So as a result, the whole system doesn't work at all, and your user is unhappy. In contrast, reactive system or reactive Goose is basically the Goose that reacts to all the changes. So you say, do this, and it changes its states. And then you say, do that, and do this, and do another one thing. And all the time Goose changes its state in order to feed the current environment. So basically, you may imagine the microservices system that reacts to all the changes. If one service disappeared, we added another one. If external system doesn't work, we added fallback or something like this. So we immediately reacted to the changes of the environment. So this is about reactive and non-reactive. But yeah, it sounds really funny and cool, but our talk about reactive streams and not the system. We are going to recall the connection, or how reactive streams mirror it, or reactive system mirror it in reactive streams. But this talk is about reactive streams. And reactive streams and the history of reactive streams started with the UI. And it started really far in really far 19s. And you may wonder what happened at this period of time, basically. Basically, at this period of time, big companies like Microsoft, like Macintosh, started a competition for the next era of computers, and computers for users, for everyone. And the main problem that they try to solve at this point in time is how to give a responsive user interface to everyone. And it means that before developers was building, I don't know, really straightforward application where you got a function, you call this function, you got a result, and nothing else, but like nothing more complex. So yeah, they were building complex program, but it wasn't related to some actions, to some inputs from different devices. And right now they started building applications for computers, for users. And the main idea, main problem for that is how to build UI and applications that are responsible, that gives users the best, the most comfortable usage of it, using user interface, using mouse and keyboard. And in order to understand the problem, let me quickly show you a simple demonstration. So prepared a simulation of such an application that the user of kind of the past generation tried to build. And this application is pretty simple. So the application lets you drag and move a box on your screen. So you can imagine or recall it with moving icons on your Windows screen or something like that. And what the engineer of that period of time could do, and basically was doing, is writing functions. So I'm using JavaScript for that purpose in order to simplify user interface and so forth and so on for this simulation. I'm using JavaScript. Don't blame me. Yes, I'm Java developer, but anyways, they build functions for reacting to particular actions. And since the API of this period of time, of the system of this period of time, didn't give them a way to react to events, the simplest they could do is writing while true loop. So you can assume that set interval is almost while true loop, and they basically, what they could do is pulling some data structure like a queue. In this context, we are using array for storing the events. And for example, after some period of time or with some delay, we are doing the same action, pulling events, and then apply based on what type of event is that. So nothing complex. As a result, what they got afterwards is something like this. Yes, you can feel how responsive and how user-friendly this interface and this moving is. And you might remember, like almost everyone can remember, all these Windows logs, etc., related to such development way. So that was a huge problem. And of course, you can say, okay, let's try to pull, for example, more quickly. For example, once at 300 milliseconds. And yeah, it seems a little bit better, but not the best. So we can say, okay, let's try 100 of milliseconds, and let's reload this guy. Yeah, seems a little bit better. So let's put 0 because we can. And of course, 0 will be super smooth. But then we have to ask a question. Wait, we have a CPU, and if we are going to spin every without any delay, we are going to spin a single CPU, because at this point, at this period of time, our computer was single CPU with a single core, so we can run only a single operation at a time. And if our program is going to occupy CPU, we won't be able to run anything else, and this was a huge problem. So we can't simply just occupy the CPU and without running anything else. And yeah, that was the problem that engineers faced at this period of time. They started thinking, and actually they found an answer. And that answer was well-known observer pattern. And it was interesting that Windows, Microsoft, published in PC Mac in 1992, a post that they developed a really great event-driven API for their Windows application developers. And basically what they've done is changed everything. And they develop, of course, observer pattern, but that observer pattern changed application really well. And the responsive, being responsive, like the application started being responsive. So let me show you that we still have unresponsive API in case of pooling model with some periodic pooling. Now I'm going to change the application to push model or observer pattern, because observer pattern is basically a push model and representation of push model. And we didn't change a lot. We're still using the same functions, but now what the API of system give us is ability to set a handler. And these handlers will be invoked once we got some signal from mouse or from keyboard. And this signal will immediately appear at our function, so you will be able to react to the event timely or in time, on time, without any delays, without any pooling. So we'll listen instead of checking whether we have something in the queue. And all the things is hidden inside the system and is really efficient. So let me show what happened. Basically, we got really responsive and smooth applications. So which changed the application developments in a good direction. And let's recap it. So basically what was done is introduction of observer pattern, which was ability to set a function and some listener, for example, and mouse move. And our goose approves this or such way of development application, because right now we can easily react to anything like mouse dragging and so forth and so on. Seemed good, but we got but. And it turned out that we have to develop not only a simple dragging of icon or of the box on our screen, but we have to develop something much more complex than a simple icon dragging or something like that. It turned out that we got new requirements for building complex animation, for doing complex processing. I don't know what could be done with mouse click or mouse dragging, but it happened. Let's consider this simple case. We got a requirement to build complex animation. And it's, from the first glance, it seems really easy to develop such animation where we have a couple of objects on the screen and they have to react on mouse move and so forth and so on. But it turned out that development of such application is much more complex than it seemed. And developer ended up with the code like that. Yes, really clear and transparent code that does this simple animation. Of course, we ended up with what we ended up, and you may see, okay, what the hell is going on the screen? But yeah, that's the code which is working and reacting to all this stuff, and it's not really good. And what happened is basically the new problem appeared on the horizon of engineering of this period of time, and we started had to develop hard and complex processing of events. For example, you have to build some mask, I don't know, execution, or you have to build Excel of this period of time. So you have to execute a sequence of actions, and you have to build kind of a set of observer that reacts to another observer, and so forth and so on. And it's really hard. On the other hand, once you started building that, it's almost impossible to build clear and transparent code. So we started losing the understanding of what's going on in our application, which is really not good. Fortunately, we found a problem, and in 1997, Connell Elliott with Paul Hudak ended up with great solution which got a name functional reactive animation. And basically, we started with reactive system, and this is the second time where we mentioned the word reactive in the content of streaming, of programming. And basically, reactive animation in its essence is ability to write clean code using some DSL functions and data structures for building complex animation which are a result of, for example, mouse movement. And you can see this 3 line of code which does the following movement of three objects with a delay, which is amazing. So it means that you don't have to write a ton of code, and some DSL, some framework is already providing you with pre-created structures and functions which just let you use them, and that's it, which is amazing. And it seemed that we got a great result. So we got observer pattern, we got reactive animation, and they all solved all the problems of this period of time, because now we can easily process synchronous mouse input, keyboard input. We now can easily build complex transformation, data processing, which is not a problem at all with reactive animation as a language for that, or DSL. But it turned out that, again, we are moving and time moving, and we got new requirements. And it turned out that now we are in 2000, or we are in millennium. And you may associate word millennium with 2 things. The first one is, you may think, okay, maybe Windows millennium. Yes, of course, yes, but yeah, no, it's not the main things that we are going to focus right now. The second thing which is started appearing in the horizon of engineering is service-oriented architecture, or we started building distributed system at this period of time. Because You may remember that in 19s, everyone was using the single computer for doing everything. So every engineer was thinking about a single computer and communication within a single computer, because we all assume that, for example, interaction with memory, like with active memory and your CPU is almost cost nothing, so it happens almost immediately. So nobody was thinking about anything, and the execution of function was almost immediately in terms of sending a signal. On the other hand, during this period of time, the scientists started building distributed system communication over the wire. The TCP protocol appeared. So in millennium, the companies started using this technology and started building distributed system. And what happened is basically we got a new problem, and this problem related to how to build efficient networked application that does communication really efficient. And let me show a small simulation again to show you what happened at this period of time and what problem could lead to ignorance of all these changes. So let me open this my Visual Studio Code again, and let me show you this following simulation and the following environment. And first of all, let me do a short intro of what's going on the screen first. So yeah, on this screen, you can see a couple of things. So first of all, we have a box with timer, which basically let me run or stop my animation or simulation. On the other hand, I can easily control the velocity or speed of the animation in order to explain what's going on right now in terms of communication between service A. So here we can see this white guy on the left side or white line on the left side is basically service A, and this purple line on the right side is service B, for example. Or you can imagine that this function, which is sending a call from one service from client to service. And on the bottom or at the bottom of the screen, on the left bottom corner, you can see the requirements. For example, you can imagine that we have to get 20 elements or more elements, and we have to figure out whether this elements fits the filter or anything that user set up. So we are requesting elements one by one, and since we are assuming that communication is happening or execution or call happens immediately, we are saying that, yeah, there is nothing in terms of delay here. While on the other hand, we have a few more parameters here. For example, the lookup time of elements is for example, some value. So let me show you what's happening. So basically, we are sending, and once the element is finding right now, the service is blinking. So you can see that we send a request and we ask him give us an element, and the service is blinking, so which means that it is looking for something right now. So it's just for the purpose of explanation of what's going on the screen right now. And on the other hand, we have some time which is taken for element processing or figuring out whether these elements good for us or not. So it means that, for example, we are requesting and then we are thinking whether, oh yeah, yes. No, it's not elements defined. It's something, yeah, this parameter. So right now we requested, and you can see that we are thinking really long in order to figure out whether this element is good or not. So this is the parameters which we have right now in our system. All right. And finally, let's run this simulation again. Let's make it faster, and we can see that simulation takes 10 seconds in order to process 20 elements, which means that this time which is taken for processing, it's important because then we are going to compare different technique and how, for example, different parameters of networking communication affect this time. All right, so now we we can see that, for example, this simple communication within a single machine or single computer takes 10 seconds. And now we are going to add a network in between the services, which means that we have some changes. And the first changes which appeared with network appearance or communication between services over the wire is latency. Every network communication has a delay in terms of sending a request from point A to point B, which in this case is, for example, 1 second, just in case. We can put any number, but let's put 1 second. And now we can see that the request is taking some period of time to be delivered to service, from service A to service B, and the response takes some time to be delivered from service B back to service A. And we can see that on the animation. So the square is basically a request, and the flat line is a response. And we will wait for almost a couple of minutes. Of course, we are not going to do that. We will try to run it faster, but it won't change the case that much, because again, we have to make lots of hops between services, which takes on average 2 seconds, which is absolutely wasteful, which is a huge problem. So networking became a huge problem. And you may thought, okay, so we can solve this problem really simply. Instead of trying to go from service B for one element, for a single element to service B, what if we can ask for everything that is on service B and put it in the memory? Yeah, it may work. So what they tried to do is basically the engineers of this period of time tried to cache, let's call it caching, because it's basically caching, to cache all the information from service B on the service A, so we don't have to go to make more hops over the wire. So basically you can see that we send in request, the service B preparing all the elements, because it takes some time to collect all the elements, to plug them into, I don't know, package or frame, and then we send them back. It took 4 seconds, and we are processing them and trying to find what we are needed at this point in time, and then it took 7 seconds, which is pretty efficient, which is much better than we saw before in terms of communication over the wire. However, it seemed much better, but we have some but in this communication again. And okay, it could work in case we have just a couple of kilobytes of data on the service B, which is fine. For example, 10 usernames in the database of just started application. But in fact, sometimes we have to send megabytes of information, or 100 or 1,000 or tens of thousands or terabytes of information over the wire. And in that case, it basically won't fit into the network bandwidth. It would have to be split on a couple of packets of frames. And in this case, it would lead to the following communication. So let's change our constants, and let's add to our communication something like network throughput, because it's a real parameter. And just in case, let's put 23, which means 23 elements in this simulation. So basically, we can deliver at a time only 23 elements, which means that the communication will be changed again. So we still have to collect all the elements, but now we have to put 23 elements in the first frame in order to deliver it. Then, we have to wait for a full message in order to start processing it. We can't just take the first packet and start processing it. We have to wait for a full message to assemble it back. And we have to wait, which takes some time, and only after that we can start our filtering and finding what we really need, which increases the delay or the latency or the processing time of our program a little bit again. You can see 7 versus 10 seconds. But it's not the end. Finally, in every application we have memory, and it's fine again when we have just a couple of kilobytes of information which we can fit into the active memory. But in fact, what if we have to handle a terabytes of memory at a time? We won't be able to cache everything on our computer real simply. So let's put this parameter here as well. let's say, okay, the memory capacity is 23 elements. So once we ran our simulation, we will see that there is box called memory. Yes, along with other kind of controllers here, we now can see memory capacity, which represent how much memory is available right now on the service A. And once we've done a request, service B prepared a response for us, started sending. The first packet fit into the memory because we exactly have 23 megabytes for 23 elements, which is good. But the next packet will basically crush our application with out of memory because we don't have enough memory for handle that much at a time. It means that, again, we have a problem of how to fit all the requirements of our computers, which is a huge problem. So basically, it turned out that we can solve this problem again. And what people ended up got a name batching. You all know batching because it basically means that we can simply split our communication on batches, on portions. It means that if we know that our memory capacity is 23 elements or 23 megabytes, let's request a packet that has only 23 elements. This is a simple contract, and it basically solved part of the problem. We got requested for a package, we got the package back, we processed elements because we have to sequentially process all the list of items. And if we see that there is not enough elements in the first kind of batch, we have to send another batch request and then process elements and maybe send another batch request. Yeah, it's better, but again, behind the filtering is hidden random function, so we can do 2 hops or we can do 3 hops instead of 2, which will take, again, a few more seconds to find what we really need. Again, so we saw everything in the communication of this period of time and the solution that people tried to apply it in order to solve the problem. But in general, all of this problem wasn't ideal. They wasn't golden for doing really fast and efficient communication. First of all, pulling one by one model wasn't efficient at all. Network bandwidth didn't allow us to take and cache everything, and basically our memory and computer capacity wasn't elastic or unlimited, which required us to take a small piece of data and request more, and then take another piece of data and request more and more. So that wasn't that good. And basically, at this period of time, Microsoft started building their Azure platform. And this project was led by Eric Mayer, not exactly this project, but in general, Microsoft started developing their cloud system, called Azure, and they needed what they ended up that they need really efficient communication between their services, because in their case, they have to send terabytes of data between services, and they have to do that really efficient because user won't be happy having something really slow. And Eric Mayer was thinking with the team how to solve this problem and how to make communication between services really efficient. And what he ended up with was basically changing pull model, which is batching and get all, to push model, which solved all the problem we saw during this simulation, the previous simulations. So let me show you how changing again and using pull to push improve the response, the communication and the time and the latency between services. So let me show you the next simulation, which is called streaming, because this is basically the beginning of streaming. And let's see what happened. Basically, we still send in the first request, like we are ready to receive data. Give me a stream of data. And then service B, instead of sending elements in a batch or sending all elements at a time in a single packet, started sending every found element as a single packet at the time service B found it, which means that now we are sending all the elements asynchronously. Now it means that while the first item is sending, or the second item is or element is sending, or for example 10 first elements is sending, we are looking for others, and we are not overwhelming the bandwidth of the network because everything is asynchronous and we have capacity for a few more elements. So while the element is delivered, we are immediately starting processing it because now we don't have to wait for a full batch, which delay the first interaction between services. Once the service found the first, immediately send it, we can process it, which is pretty efficient. And on the other hand, since we are processing elements ongoingly at runtime without waiting for the full batch, we don't have to keep everything in memory. We found it, we send it further, for example, in the browser or somewhere else. So we don't have to keep everything in memory, and we can efficiently use our resources, which means that we can process and keep everything pretty efficiently. And as you can see, the latency or processing time right now, 5 seconds, which is twice better than batching and almost, I don't know how much, but much better than the get all, and of course better than one by one pulling, which is pretty amazing. So it solved the problem of this period of time, but we got a few more, and it seems that, okay, we can use observer pattern, applies the same observer pattern for doing communication between services, but we ended up with the same problem of unclearness of the written code, because right now we have a stream of data and we have to do really complex data processing, like storing in the database or somewhere else, or sending data or processing them somehow. So we have to write code with observer pattern, and it's complex. You remember that. So Eric Mayer started thinking about that problem, and he ended up that basically we have two patterns in our solution. The first pattern is observer, basically, which is pretty efficient in terms of asynchronous data sending. We are listening to data instead of pulling them. But the main problem of observer pattern is we don't know where is the end of the stream. On the other hand, we don't know how to unsubscribe from the data stream, or how to send that we are done with data consumption. On the other hand, the whole representation of the data that we are consuming is iterator, because we have like a stream or a list of data which we are consuming one by one. That's how it was before. But this pattern is inefficient because it's pull pattern. So we have to get data, get more data, get more data. On the other hand, we have the way how to check whether we have more elements, which means that this is the end of the stream, whilst once we got has next false. And of course, we can close iterator, and it will mean that we can easily unsubscribe from the stream. And what Eric Mayer ended up is basically combining everything, combining all this pattern, using previous knowledge from the previous generation, which is basically reactive animation. And what he ended up with was reactive extension, which is combination of iterator and observer. So once we combine observer and iterator, we can easily unsubscribe from the stream. We can easily handle data asynchronously. So he introduced observable as a source of data. He introduced observer as a listener to the stream of data, which has on next to notify that this is the next element, to notify about an error over on error, and notify about terminal operation or the end of the data over on complete. And he introduced subscription, which let you simply cancel the stream of data, which solved all this problem. It let you use asynchronous data pushing. It's right now at this point in time with Reactive Extension, it was clear how to end the stream, and it was clear where is the end of stream, and it was clear how to unsubscribe from the data. So it basically solved everything. And moreover, he introduced the DSL, so he almost copied all the data structures and functions and naming from reactive animation, which let you write amazing data processing. And for example, in order to write all of this emulation and animation for data streaming, I used reactive extensions. For example, let me show you the simulation here. Here I'm using reactive extensions for JavaScript. I'm using the set of operators, and I build all this interaction an animation for data streaming using the operators from RxJS, which is amazing. And I don't have to write this pyramid of hell in order to run the next animation after the previous and check how many animation I have already ran and so forth and so on using just simple imperative programming. No, using the DSL from RxJS, I can combine any like animation API with data streaming API and write everything in pretty straightforward and short application. Only 50 lines of code in order to build such a complex interaction between services and simulation for you. So it's amazing. On the other hand, the solution became so cool and so popular. So everyone from other platforms, initially the Reactive Extension was developed for .NET, but a little bit later, everyone from other language platform decided to build the same solution with the same API, which means that everyone who knows Reactive Extensions for JavaScript can easily switch to Java or Swift or whatever other languages, which is pretty amazing. So let's summarize what we saw during this part. Basically, it seems that we are done because right now, Reactive Extension solved efficiency problem. We saw that during the first simulation that we can send elements, the same amount of elements in 5 seconds. And the latency between services is pretty small. And the development using reactive animation and using Reactive Extension API, we can solve complex asynchronous data processing problem really easy because now we have the same set of operators for doing that, which is cool. We saw we were thinking it was amazing, but we got another bug in the history of evolution of reactive programming again. And this bug related to the fact that we considered only a couple of cases. And unfortunately, Eric Mayer considered only a case where one consuming elements really fast and another producing elements almost with the same time or a little bit slower. And there is a few more cases in communication between in distributed system where, for example, your producer can send elements really fast, but consumer can process them in a really slow way. So basically what appeared is the following problem. Let me show you the simulation again. And first of all, let me open the constants again and change the behavior of our system a little bit. We remember that the lookup time is 60 milliseconds and the processing time of received elements is 30 milliseconds, which means that almost the producer twicely slower than the consumer. So let's change this behavior. For example, let's add 1, 0 to let's make our consumer five times slower than the producer, and let's see what will happen if we change this behavior in communication. So basically, we can see that the element sending is the same, the element receiving is the same, but now the element processing has changed. So we processing elements really slowly. So let's unslow that. We can see that we are slowly processing elements while the producer still producing elements, produce them, which led to out of memory, basically. Which means that we got the same problem that we got before with give me all without saying how many elements we are ready to consume at a time, which basically a problem again. So let me summarize what we saw. Basically, the problematic of the next generation of systems, which wasn't considered or taken into account by Eric Mayer, is slow consumer or slow subscriber and fast producer, which basically leads to crashing of the application. And on the other hand, as you may remember, the Reactive Extension was really popular in different platforms. But you may think, okay, in JavaScript, we have only a single-threaded application, which means that behavior of particular operators from RxJS works in some particular way, in a single-threaded way. But once the developer once JavaScript developer switch, for example, to Java, which seems similar, you know what I'm saying, it appeared that the same operators works absolutely in a different way, which is a problem again. So the next problem that appeared to engineers of Reactive or users of Reactive extensions is that single parting behaves really differently in different platforms. And even more, within, for example, single JVM, different implementations of Reactive extensions or similar libraries were working in absolutely different ways. And it became that we got the next problem. It turned out that we have to somehow combine all of these libraries even within the single ecosystem, which is another problem. So what we really needed is to solve those problems. And the engineers from different companies like Microsoft, like Netflix, like Twitter, started thinking about how to make all of these cool Reactive extensions better in terms of stability and better in terms of compatibility between them. And they solved this problem. And the solution for this problem got a name, Reactive Stream Specification. So basically, Reactive Stream Specification is simple idea. What they done, what the people from the engineering group who was working on who were working on this problem done, they basically combined. They took the solution from the history, from the past, and they had taken batching and combined batching with Reactive extensions, with asynchronous streaming, and they got Reactive Stream Specification. So basically, that's the idea which is hidden behind Reactive Streams. And what they've done, a part of that, they introduced the set of standard interfaces, like Publisher, which has a single method subscribe, which recalls with observable, of course. They introduced Subscriber, which again almost similar to Observer from Reactive Extension, but right now we have method onSubscribe, which basically receives subscription. And as you can see, subscription has, along with cancel, it has a method request, which basically a representation of a user starts sending data to its consumer, which means that now we can easily control how many elements we are ready to consume at this point in time. So this solution solved, first of all, preserved a RIX push model, so it means efficiency. Now we got, in addition, a synchronous batching or pull-in model. So right now it's combination of push and pull model. And a part of that, we got a standard set of interfaces which should behave in every environment identically, which is basically amazing. So let me show you simulation first of all in order to ensure you that this solution solved everything. So I keep the same configuration of the environment as before. And right now I'm changing streaming to Reactive Streams. And now we are going to see what happened. First of all, let me slow it a little bit. First of all, as I said, in order to start communication, subscriber has to specify how many elements it is ready to consume at this point in time. And since we know that the memory capacity is 23 elements, let's request 23 first element. So that's what we are doing right now. We are requesting 23 elements, and then the producer starts producing 23 elements in the same way as before. I mean, in the streaming way. So it means that every element is sent independently from another one, which is pretty efficient. We know that. And then the consumer fill the memory with all the elements, slowly consume all the data. Let's emphasize that a little bit. Consume data, you can see that producer doesn't produce elements because we doesn't request. But once we know that we are good for the next batch, with the next set of elements, for example, we can asynchronously request more, because Reactive Stream Specification says that we can request elements asynchronously, which is amazing. It solves all the problem. Now we're saying, give me, for example, 18 elements more, because we know that right now we have 5 more elements in the memory, so let's request 18 more, and we know that the communication will take 2 seconds between sending request and receiving the first response. So we will be able to end up on time with the rest of the elements once we receive the next batch from the producer. And then producer produced elements, and we can continue consuming and processing elements, which is super cool and super stable, first of all. And as you can see, it is efficient. Yeah, we request the next batch, but once we are going to change the parameter back to the initial one, when we have really fast producer and fast consumer, we will see that even though we changed our model to push-pull, we are still efficient. And we will take only 6 seconds in order to, or 7 seconds, in order to process all the elements. And as you can see, we are sending requests for next batching asynchronously one by one without stopping, which keep us our stream stable without any delays, which is really cool. All right, so what happened next is basically the Reactive Streams started being popular, and nowadays we are having tons of different implementation in different languages market. First of all, we got adoption for different platforms. Initially, Reactive Streams specification were developed for Java, but then it was adopted for JavaScript and for .NET and for many other different platforms as well. Apart of that, it appears that we have many different implementations. The first one was Akka Streams, then appeared Project Reactor, then RxJava became the next generation of RxJava provided additional support for Reactive Streams as well, and we got implementation for JavaScript and for .NET as well, which is pretty cool. And we can use the same Reactive Streams in many different platforms. And even more, it became a standard for Java and Java's standard Java library, which means that starting from JDK 9, we can use the same set of interfaces Reactive Streams from Reactive Streams specification in order to use it from the JDK immediately without bringing any additional libraries into our application, which is pretty amazing and means that the standard became super cool and super useful for everyone, not for just a part of user, but even for the whole Java ecosystem, which is amazing. All right, so let's summarize what we saw. Basically, sound really great. It seems that we solved all the problem on the market. And now Reactive Stream specification is a standard for messaging in Reactive System. I'm saying Reactive System because now the streaming specification can react to different changes. For example, producer can listen to consumer needs, and it won't overwhelm the consumer because it doesn't know what is the state of it. So it means that our Reactive Streams can fit the requirement of Reactive System and make it stable and really efficient. A part of that, it affected, of course, stability, because now we are using the hybrid push-pull API, which means that, again, stability and efficiency. And it seemed, okay, we solved all the problem, but we got another bug. And this time, the bug in the history was related to us, to engineers. And the problematic of nowadays, basically, is that we all engineers, we all developers, but we don't want to solve problems. We want a new, shiny framework to try. Of course, that's what we want to do every day. You don't want to write and solve the problems. You want to try new cool solutions and frameworks. That's what we want to do as an engineers. And of course, it affected reactive programming and Reactive Streams, because Reactive Streams is something really complex in terms of development. Of course, it's simple once we are using map or take operator or a single flat map in our single application or data processing stream. But then it can simply happen that we have to add another flat map and then another flat map, and then we have to shoot a couple of times in the lag because something happened and we can't figure out what happened and how to debug that. So that's what happened basically with reactive programming. And reactive programming became really complex in terms of debugging and writing code and in general figuring out what's going on in this piece of code. even though it's pretty short. And what developers wanted to do basically is something imperative. And it happened that imperative is not that. So basically long live imperative and what we saw before. But in order to solve all this problem, Microsoft started doing some progress in this direction. And the Microsoft started doing this pretty far in 2010. And what Microsoft introduced basically, as far as I remember, Microsoft was the first, and C# was the first language which added async await. But basically, in order to make efficient asynchronous non-blocking communication between services, pretty simple in imperative way, they added something called async await. So async await, if you don't know, is a way to pull an element or kind of listen to some changes or something which is asynchronous without creating a function. So the internals of the system does it for you. And this paradigm became super useful and simple for everyone because we love imperative programming because of simplicity. And it happened that one of the user of reactive extensions in C# asked on the network whether reactive streams is alive at all at the time of appearance of async await. And the author of one of the maintainer of the core library of C# answered, yeah, we are working on reactive extensions, but we prepared another solution for you for asynchronous streaming, call it async enumerable. You can see that, which means that now we can avoid reactive extensions at all. I mean, at all. So basically what they introduced is asynchronous streaming, which basically let you write in something like that. So as you can see, this is pretty imperative code. Nothing about streaming at all here. But if you're going to look at every line of this sample, you will see that we create a synchronous enumerator, which is basically a synchronous queue or a synchronous stream. It could be anything. We can asynchronously put elements into the queue, and on the other hand, we can asynchronously consume them, which means that we can be really stable because this is a queue. We can say, okay, send us 23 elements asynchronously, and then we can asynchronously consume every element using imperative programming and using await keyboard, for example, because now instead of creating a function in order to listen for an element, we can say await, which means that the internal state machine will interrupt and will run another code and will be back once the element appeared. So the next line of code will be executed only and only when we get the element, a notification about appearance of the element. And then we can consume a couple of elements using while true loop because we can check whether we have next and next elements. And once we got the end of current batch, we can say, okay, let's back to await again and wait for the next element or a few couple of elements from the service B, for example. So basically, it solved the problem of complexity of reactive programming and reactive extensions. And we don't have to use functional programming because functional programming is somewhat complex. And we can still do efficient streaming with imperative programming, which is kind of solution for everyone. Yeah, sound good. And even more, async await started appearing in different languages. For example, it appeared in .NET ecosystem, but then we saw async await in JavaScript. Yes, there is async await in JavaScript standard specification. And then we got Kotlin. And Kotlin also offers us somewhat similar to async await, async suspend, which is somewhat similar for Java ecosystem and for JVM ecosystem. So this is, and a part of that, we will have something similar to Java, which is super worrying for every reactive streams programmer, because in a couple of years, in a year or I don't know, in a few years, we will get, or even sooner, we will get somewhat called Project Loom or Fibers or continuation, which basically almost similar to async await, a little bit simpler paradigm, but it means that using this project, we will be able to do asynchronous non-blocking execution on functions or streaming without using functional programming for that. We will be able to simply run function which could be a communication over the wire and receive a feedback without blocking our threads, which is somewhat we were looking for a couple of years, which is cool. So it led to the next question. What will happen with reactive streams? And will reactive streams and reactive programming and functional programming has any future at all then? This is a good question. But in order to understand, we have to understand the trends, the direction in which we are moving nowadays. And one of the directions in which we are moving is GraalVM, for example. For those who have never heard about GraalVM before, I will do a short intro for that. GraalVM is basically two things under the hood. The first one is just-in-time compiler, which is basically a runtime compiler which improves the runtime code, the bytecode, and make it a little bit different in order to enforce your application and make it much more faster. That's why our Java application is pretty efficient compared to maybe the same program in C++, because our application is running and improving itself at runtime. In contrast, C++ doesn't do that, or other programs that doesn't have just-in-time compiler. On the other hand, GraalVM is polyglot language or polyglot platform, or it's basically ability to run different languages and platform for running different languages on the JVM, which means that now you can run Python, Ruby, JS, or I don't know, even it's possible to run C# on top of GraalVM, which right now means that all these languages could be combined really easy within the single platform, and they could really easily communicate with each other without any boundaries, without any problems at all. So it leads to a really good question. First of all, let me show you a short demonstration of that. Before I'm gonna say anything else, I'm gonna show you that this is really possible. And right now, yes, let me show you the simple TypeScript code, because yeah, I'm Java developer. I don't really like JavaScript. That's why I'm using somewhat in combination with JavaScript and static compiling languages. So I'm using TypeScript in this case. And here you may imagine that, for example, you have a case. You want to move from your legacy JavaScript application to Java world, and you want to do that almost immediately, almost right now, and you have like a big enterprise application, but it means that once you have big application, you have to write everything to, for example, Java platform, or vice versa. You want to move from Java, one part of Java application, to JavaScript because of non-blocking and efficient single-threaded data processing and simplicity of JavaScript. So it could be, it may happen that you have to move from one to another platform. And what you can do at the very beginning, in order to start using JavaScript right now, you can easily use, for example, from JavaScript, your Java application. So here I have a simple Java application. Yeah. A simple Java application, and here is JavaScript application. But before this point, I have to, I remember that I have to finalize my statement. So you can run different application within the single platform. So you have to ask the question, and here is a good question basically. If you have, for example, a sync await in JavaScript, and you have a sync await or something similar in Java, or for example, if you have a sync await in Python or any other languages, how are you going to combine them? Do you know what guarantees is hidden behind a sync await in C#? Of course, they have their specification, but for C#, it doesn't mean that they have the same guarantees for other platforms, because implementation in Java could be totally different, or implementation in Kotlin is totally different. And now the question is how you are going to combine them all. How are you going to to use an API of a sync await function from one ecosystem and another? That's a good question. And unfortunately, there is no answer for that because it may happen that behaviors are totally different. However, if you are going to look at reactive streams, you will see that reactive streams is a standard. It's a specification. We specify all the behaviors. And if you're going to look at the link on the reactive streams webpage and specification document, you will see that all the behaviors are specified, and there is some specific guarantees which specify how do you have to call on next method, or what will happen once you made a request, and so forth and so on, which is good because standard is a standard, and it means that standard works similarly everywhere. And the power is in the specification. Yeah, that was said by one of the Java architecture, but it's a good statement, which means that we can use reactive streams in order to build standardized and predictable communication between different platforms. That's what I want to say. So let's go back to our simulation. And as you can see, here is a piece of code from Java world, from JVM world. Here I'm using project reactor, basically, and reactive streams in order to generate stream of data. This is a really simple stream of data from Java, and send it and receive it, basically consume it in JavaScript. So let me open my VS Code with my JavaScript. And as you can see, using Growl API and Growl VM, I can easily say, okay, please run this Java application and let me access to the created object, to the loaded object by JVM. And then I'm using reactive extensions at this point in time. I wrote an adapter for converting reactive streams to RxJS. And here I'm using RxJS API in order to consume the stream and process it. And right now I'm going to run it. So in order to run such an application, you have to use Growl.js built into Growl GDK standard library. Unfortunately, I'm not the guru of all this stuff. I just compiled everything on my local machine. In terms of, I compiled Growl.js. On this question, Oleh Shalaev can answer you. But yeah, let's postpone them. And in order to run it, you have to first of all specify what libraries you want to load in your VM, and then you have to say that you want to run node ecosystem, and then you have to specify which file you want to run, which is basically index.js, which is the code you just saw before. And once you're going to run it, you'll see the output because I'm logging everything. And what happened here? Basically, I'm logging all the actions that happens in my Java application, as well as I'm logging everything which is happening, which I'm receiving here. So on every element I'm writing, I got an element. And if you're going to look at our console output, you'll see that on every element, on every next, we're receiving, I got an element. And even more, all the signals are mirrored here. So if you're going to look at request execution, we will see that our JavaScript application send request and receive next couple of elements, which means that right now we can easily combine totally different application just gathered by a single specification, which guarantees absolutely the same behaviors, which is amazing. So even though you will try to parallelize this execution, you will get benefits because, again, reactive stream specification works in the same way. And yeah, you can believe me, I can easily change, for example, something here and recompile in order to ensure that this is a real code. For example, I can add mapping here and say, okay, I want to map integer to a string, for example, hello world from Java or from GDK, let's call it GDK. Hello world from JDK, and instead of publisher integer, I can return string, which is simple. And I can reassemble my application here to the new jar file. Yeah, it's reassembling right now. And yeah, I can simply rerun it. Yeah, I'm rerunning the same application. And here you go. We got something happened. Let me check what's going on there. Basically, yeah, we are consuming do work. Yeah, let's do instead of do work, let's do what is the name of the method that I changed? This simple work, right? So yeah, it will ensure that I'm not fooling you. So I just changed this piece of code, and right now I am recompile my TypeScript because yes, this is TypeScript. I have to recompile it in order to compile it to TypeScript. Yes, this is the command that I want to use. Yes, it's compiled. It's fine that it's erroring. Yeah, don't worry about that. It's fine. It's JavaScript world, so it will work. No worries about that. Yeah, I recompiled my JavaScript file. So if I'm gonna rerun this application again, I have to see a new message from my Java world. Yes, I got it. 96 hello world from JDK. Perfect. Which means that I just recompiled my Java application, my JavaScript application, rerun it again, and it worked. Again, with the same behavior, with the same Reactive Streams guarantees, with the same stability, which is really needed for our application and for this standard API, which means that you can easily combine totally unrelated languages with the same behaviors, which is cool. I like it. It's fun. So let's go back to our presentation and say, okay, sounds good, but in fact, nowadays we are building microservices. Not that many companies are trying to use Graal VM platform and try to combine different languages. I know only a couple of companies, big companies, but in any case, there is only a few users of this big feature and great feature. But unfortunately nowadays, or fortunately nowadays, we all build in microservices, which means can we use Reactive Stream specification for data streaming with the same guarantees between different services? And fortunately, I would answer yes, we can. And we can do that with reactive sockets or RSockets simply. This is basically the project on which I'm working on. And RSocket is implementation of Reactive Streams and this specification as a network protocol, which basically gives you an ability to use Reactive Streams in different platforms with different libraries, send messages over the wire with the same behaviors, using any style of communication with any format because it's binary protocol. And the most important, on top of any transport like TCP, WebSocket, HTTP, or ARON. So you can do anything without changing your code. So let me show you the following demonstration where I'm basically combining three ecosystems. I'm using Graal in order to run my server. So it means that here I have the same Graal RSocket application, which is used in my Java demo application. So basically, I'm using Graal in order to access my legacy Java code, or vice versa, try to use Java Future instead of having single-threaded JavaScript, for example. And then I'm running RSocket server in order to expose a port for my clients. So that's basically what I'm doing here. And everything is Reactive Streams. So RSocket provides its own Reactive Streams API and library, call it Flowable, but it doesn't matter. It just works. And here I'm having RSocket client, which is basically a browser application. So what I'm going to do is I'm going to change this Reactive Stream simulation to RSocket. That's what I'm going to do. And here I'm using, again, the same Reactive Streams in order to connect to my server, in order to open my browser and consume the stream of data from the server side, because here I'm exposing a single request stream handler. There is a couple of more, like request response and so forth and so on. It doesn't matter for this point in time. And then I'm requesting request stream, and then I'm requesting simple work, or ask for doing simple work for my reactive service, which is basically Java application. So I'm trying to combine three different ecosystems in a single simulation. So let me show you what will happen then. First of all, I have to run my server. So I have to use our socket.js server in order to run my node server and JS application with Growl. So it's running right now. It's good. And then I have to open my browser. So I open in my browser, and since I'm not showing any animation at this point in time, I will show you the following. Let's go back to our client's code, and let's see what will happen. As you can see, I'm using subscribe in order to subscribe to my stream of data. And as you can see, there is 4 methods specified by specification, like unsubscribe, on next, and on complete. And what I'm doing right now, I'm basically trying to hack the environment. And instead of saying, okay, give me, for example, 10 elements, I want to control my subscription externally. So I'm storing my subscription in the field subscription my, which is basically right now is accessible from console. And as you can see, subscription my has request method. And now once I'm going to call request one, I will receive a single element, 0 hello world from JDK. Amazing. And if you're going to look at our output, you will see that this request totally identically mirrored in our publisher, because you remember that we are logging all the messages that we receive here, which means that we are going to log the request method. And it means that right now from the browser, we ask for a single element, and our producer or publisher has produced exactly a single element, and we received it. And yeah, we can request 10, for example, and we will receive 10 elements. Perfect. It works. And we can request for 100 of elements, and we will receive all of them, and then we will receive done, which means that right now we can easily communicate between totally unrelated platform over the network, over different microservices with the same behavior, with the same standardized specified guarantees, without losing anything like stability, which is the most important part of nowadays communication and enterprise system. This is pretty cool. I like it. And even more, yeah, let me finalize all this statement. The main question that right now is popping up in your brain is, okay, so do reactive streams have any future at all? So can we use reactive streams? What will happen then, even though we have such cool libraries? Basically, it has future. It has future even for developers that are afraid of hard things and complex things, because we can combine different platforms. We can use reactive asynchronous streaming, for example, from Kotlin, or we can use async await from Kotlin in order to consume reactive streams, because reactive streams brings guarantees, brings standard for communication, which is good. But data processing could be done in imperative way. There is nothing which prevents you to consume data in imperative way, for example, using async await. So it means that all this stuff is our friends. We can use everything in order to build simple and efficient and pretty standardized application in terms of communication over the wire and in different platforms. So basically, however, in order to understand where do you have to use all the things like reactive streams, you have to answer a couple of questions. And for that purpose, the Goose created a cube for you, because right now, yeah, it seems that we can use all this feature, but the most important is to understand where do we have to use it, because we can't use it everywhere. Basically, it's not the Goose cube. This cube were created by Eric Mayer in 2011 in his paper, Your Mouse is Your Database, because everything has the same behaviors. That's why Eric says that your mouse is your database. So it means the database has the same behavior as your mouse and should be processed in the same way. And what he says, and what he answered in his paper, is that you may use pool model, or basically if you want to use simple async await. Yeah, first of all, let me introduce what is in this cube. basically there is a couple of edges in this cube. The first one is volume, or the data size, which means that how much data do you have in your services, in your system. And if you have small data storage and you doesn't have that much data to send between services, then you have to go to the top corner. On the other hand, if you want really fast application, then you have to consider between pull and push. And of course, you have to understand what is data structure and system you have in your application. So basically, if you use key-value storage, then you can gain some benefits. And if you use private relative data storage, then you will lose something. So what he says in his paper is basically if you don't have that much data, if velocity or latency is not the most important requirement, and if your data storage is if it is have complex relationship, then most probably you want to use async await, and you don't want to complicate your application with functional and reactive programming. On the other hand, if you want to achieve really fast application, if you want to achieve low latency, then if you have ability to use key-value data storage, then most probably you want to use reactive extensions, because reactive extension, as you might remember, is simple data pushing. So it's stream of data without any boundaries. However, if you want to build flexible, standardized application which is pretty close to reactive system, which let you build reactive system basically, then you want to use reactive streams. Because if you know that there is fast consumer, fast producer, then you can easily change your reactive streams to work in push model by requesting load max value. This is a magic number which turns the behavior of reactive streams to reactive extensions behavior, to the simple push model. But if you know that the guarantees in communication between service B and C are super important, and you don't have to lose service C because of high intensive data stream from service B, then you can easily change it and tune it using push-pull model from reactive streams, which is amazing tool for you. All right, so this is basically it. Let me finalize what I said. First of all, the evolution of reactive streams started a long time ago. It born in the era of UI, and found in a place of enterprise, and found a place in the enterprise world, because we started using the same patterns and features that were developed for UI in order to build microservices and distributed system. And finally, the standard of the specification started being a standard for building a reactive system, because you remember, reactive system is a system which reacts to all the changes of the environment. And with reactive specification, we can achieve that, because our producer can easily react and listen to the consumer needs, as well as the consumer can notify producer about its readiness to consume data, and so forth and so on, which is somewhat really close to reactive system. And of course, standard is always standard, so we can use it everywhere in different platform and ecosystem and combine them without thinking what behaviors of this ecosystem and what behaviors of that ecosystem, because reactive stream specification give us some guarantees, which is good. And finally, we have to remember when do we have to use proper tool. We don't have to use a hammer in order to nail something absolutely unneeded in this tool. That's why we have to go and look at Eric Meyer paper to Eric Meyer cube in order to understand whether our application requires async await, or it requires RxJS or reactive extensions or any other Rx tool, or it requires, for example, reactive streams. So that the final things that you have to do after this presentation if you want to use reactive programming and reactive streams. So that's basically it from my side. If you want to learn more about Reactive Programming, please join my Twitter. All the simulation and demonstration are available on the GitHub. So if you're curious about what is going on under the hood and how I have developed all this simulation, please visit collaboration in encapsulation group. So let me quickly show this. Let me quickly show this link, and there is the state of Reactive Streams emulation, which basically incorporates all the demonstration that I have shown during this presentation. And finally, if you want to go deeper in reactive programming world, I'm giving a course at Go-To Academy in March, in the end of March. So please join us if you want to learn more about reactive programming and building reactive system using Spring, Java ecosystem, and Project Reactor. So that's it. Oleh, please take the control of this presentation meeting.
Hi, Oleh. Hi, Oleh. Right. It was a journey, quite a bit of time and quite a lot of information. I'm very happy that we had this opportunity to listen to you. Just one quick question in the chat from Praveen. The question is, the place where the specs for Reactive are defined is the website reactivex.io, right?
Say it again.
reactivex.io.
The main question, which box are defined?
Where is the specs defined?
Oh, yeah. The specification, let me share my screen again. Sorry, yeah. The specification is defined in reactivestreams.org. So yeah, reactivestreams.org. This is the homepage of Reactive Streams specification, and somewhere in the bottom of this page you can find the link to the specification itself, which declares all the rules and the requirements to the communication between all the participants of, or I'm calling participants, all the interfaces of Reactive Stream specification. So please find the specification on the GitHub. And if you wonder what else Reactive Streams hides behind, go to reactivestreams.org, and this will answer all your questions.
Very good. Very good. I don't think we have any more questions in the Slack channel. If you're watching this after the whole thing has ended and you're watching a replay on the YouTube, please just, I don't know, find Oleh on Twitter. He goes by Oleh Dokuka, and ask your questions there.
Yeah, I'm more than happy to answer.
Yeah, he is more than happy to answer because he's an excellent human being and a top world-class professional. So with all that out of the way, please join the Virtual Jug Slack channel. We're gonna absolutely love to have you there. There was a question how not to miss the sessions. If you're watching this on YouTube because you missed this particular excellent installment of Virtual Jug Live, what you should do, you should click the subscribe button, and you could also enable the notifications on YouTube, and then you will never miss the session ever again, right? Because the YouTube will spam you about the next session time. So all in all, join the Virtual Jug, follow Oleh, follow myself, and we will see you probably in February. Thanks a lot. Thanks, Oleh.
Thank you for your attention. Thanks, everyone. And again, thank you for inviting me. My pleasure. Absolutely. And yeah, see you all later.
Absolutely. See you. Thank you very much. Bye-bye.
Bye.